In this video, we will talk about confidence intervals. A confidence interval is an interval estimate of a sample statistic associated with a given probability. One example would be a 95% confidence interval for the mean, which is something we see very often. This is a rather abstract definition, so let's see what exactly it means. Our goal is to estimate the population mean. So we sample from the population, n individuals, sample size of n. We calculate the sample mean. This is our estimate. And we calculate the sample standard deviation. Then we can estimate the standard error of the mean by dividing the sample standard deviation by the square root of the sample size. We always remember that although we only have one sample, this is just one of many possible samples, and our one mean is one of a set of normally distributed means in their sampling distribution. And this lets us link proportions to probabilities. More specifically, we can start with the probability. So let's say we want a level of confidence at 95%. We can pick anything. We can pick 99, 50%, 75%, whatever we like. 95% is used most often. And then what we need to know is how many standard deviations are associated with this level of confidence. As we know, 95% is associated with 2 standard deviations in the normal distribution. Therefore, this means that 95% of means will lie within 2 standard errors of the population mean because the means are normally distributed. Actually, this is not exactly correct. There is a little problem. The little problem is that the theoretical expectation is based on the sampling distribution of the mean, which is normally distributed with the standard deviation equal to this thing. So we're talking about a fraction of the population standard deviation. But we only have one sample. We only have this. We only have the sample standard deviation, which is our estimate for the population, but still it's just an estimate. This means that our estimate of standard error has an extra level of uncertainty because it is based on an estimate which itself may be off the population parameter, the population standard deviation. This means that instead of turning to the normal distribution in order to look up how many standard errors are linked to 95% probability, we have to use a slightly different distribution that expresses this additional uncertainty. And that turns out to be the t-distribution. And the t-distribution has many different versions called degrees of freedom because the extra uncertainty depends on sample size. If our sample size is small, this means that there is a lot of uncertainty associated with our estimate of the standard deviation. Our standard deviation of our sample could be well off from the standard deviation of the population in a small sample. However, if we have a very large sample, then we probably have a very good estimate for the standard deviation of the population based on our sample. So there is going to be less uncertainty associated with our estimate of the standard error. The t-distribution differs according to sample size, and in fact, we need to use n minus 1, so the number of data points minus 1 is the degrees of freedom that we need to look up in the t-distribution. Switching from the normal to the t-distribution makes very little difference with very large sample sizes, but is very important when sample size is relatively small. Let's see what this looks like. This is the normal distribution. And this is the t-distribution with 2 degrees of freedom. If we had a ridiculously small sample of 3 data points, then this would be the relevant distribution for connecting standard errors of the mean to probabilities. A more reasonable sample size of 11 leads to the t-distribution with 10 degrees of freedom, which, as you see, differs mostly in these regions. Expressing the extra uncertainty a bit far from the mean. The t-distribution with 100 degrees of freedom is really close to the normal distribution, and with 1000 degrees of freedom is essentially indistinguishable. So this is how this extra uncertainty is taken into account when we use the t-distribution to connect probabilities to proportions rather than the normal distribution. What we're trying to get at is a margin of error. What is a margin of error? It is a kind of a distance. How many standard errors away from the mean are associated with a given probability that we're interested in? For 95% probability, we want the range that includes 95% of sample means. That range is the margin of error. We know that it is roughly 2 standard errors, but we need to find the exact number when it comes to actually calculating it. To do that, we need to look up the critical value that is associated with our level of probability. Let's go look at those online apps to understand how these things are related and how you can look up in the appropriate distribution. This is the probability display that you're all familiar with. And if I choose a value of 2, which would be a z-score equal to 2, like 2 standard deviations above the mean, you can see it here. And we plot the probability of a value being inside this interval from -2 to 2, we see that this is about 95%. We could try to see the same on the t-distribution. So if you click on the distribution, you can choose the t-distribution, and then you can choose how many degrees of freedom you want. And so now 2 standard deviations are associated with a somewhat lower probability of 94 point something. What we need to do now is to go in the opposite direction. We want to specify a probability and then from that derive the number of standard errors that are associated with it. So for that, we need the critical value application. The critical value application looks very similar, but what you're specifying is the confidence level. So this is the 95% confidence level, which for the normal distribution is associated with the value of 1.96. This is the number that we've been calling roughly 2. It's actually 1.96. And you can do the same for the t-distribution by choosing t and setting the appropriate degrees of freedom. So if you have a sample size of 25, that would correspond to 24 degrees of freedom, and your 95% desired probability corresponds to 2.064. If you wanted an interval for 99% probability, it would be more like 2.8 standard deviations. If you wanted a 75% probability, that would be 1.2 standard deviations, and so on. So let us go back to our calculation. To calculate our margin of error, that is how far the point estimate can be from the population parameter for a given probability. For example, for 95% probability would be about 2 standard errors, but we want the exact number, which we can look up, and more precisely, the margin of error is given by multiplying the standard error by this critical value, which, if we're talking about 95%, is going to be around 2. It's going to be less for the normal distribution and more for the t-distribution, especially with smaller samples. For example, if we have a sample with 25 individuals, so size of the sample is 25. Let's say our mean is equal to 50. The standard deviation is equal to 6. Then our estimate for the standard error, obtained by dividing our standard deviation by the square root of the sample size. So it's 6 divided by the square root of 25 is 5, which is 1.2. This is our estimate of the standard error. What is the critical value of t with 24 degrees of freedom for 95% probability? Look it up on the app. It turns out to be 2.064, just a bit more than 2. So this is the number we need to multiply with the standard error to give us the margin of error. The margin of error, which is how far off the point estimate will be from the population parameter within a given proportion of samples, that is, for a given probability. So in 95% of samples, the margin of error tells us how far from the population parameter our sample mean will be 95% of the time. And we're going to round this up to 2.5. And then what we can calculate is a complete interval. If we have the margin of error, well, the margin of error can be on either side of our point estimate. And then we get an interval of specific values. And in this interval, we expect that a given proportion of samples, however many we choose, 95% usually, so this proportion of samples will contain the population parameter. So the confidence interval is given by our mean, our sample mean minus the margin of error, up to sample mean plus the margin of error. These are the limits of the confidence interval. This is how low it could go. It can go one margin of error below the mean of the sample up to one margin of error above the mean of the sample. If we go into this by using what we've actually done, we see that the confidence interval associated with a given probability is, this is the margin of error below the mean, and the margin of error is this many standard errors. And this many is given by the t-distribution for the desired probability and for our sample size. That's how far from the mean it can be to the left, and it's exactly the same to the right. So the mean minus the margin of error, the mean plus the margin of error, and that defines the confidence interval. And if we follow up from the previous example with actual numbers, the mean of our sample was 50. The margin of error was 2.5. And if we subtract it from the mean and add it to the mean, we come up with a confidence interval, a 95% confidence interval for the mean, which is this one. This is our interval estimate. Instead of reporting 50 and saying, I think that the population mean is 50 or somewhere around 50, you can say, I report this interval for the population mean. The population mean will be in the reported interval in 95% of samples. So this is an interval estimate. It's saying that the population mean is probably there, is probably going to be within the range we report in most of our reports, in 95% of them. To sum up, the point estimate is the sample mean, is one number. The interval estimate is the confidence interval for a given probability. For example, the 95% confidence interval. It could be anything else we want. 95 is just the one used most often. This probability concerns the proportion of samples in which the true population mean will be captured, will be inside this interval. This is the interpretation of the confidence interval. It is technically not accurate to say that the population mean is within my confidence interval with 95% confidence, although that sounds very intuitive and many people actually say it. So you will encounter this. It's technically inaccurate because the population mean is a specific value and your confidence interval is a specific interval, and so the mean either is in there or isn't. So it's not really a probabilistic statement. It works the other way around. So the confidence interval will contain the population mean in 95% of samples, is the technically accurate way to state this. So the confidence interval is our report for estimating a population parameter with a range of values that will probably contain it, and is one way in which statistics not only provides an answer, but also provides a confidence associated with that answer. And the fact that this confidence is directly related to sample size means that we can adjust the confidence by changing our sample size. If we want to be more precise, we need to sample more individuals, and we can calculate how many we need and how much that will increase our precision.